Hello, welcome to our next set of notes. We are starting Unit 4, our last unit for the semester. This section we're going to cover how mathematics makes connections with music, visual arts, and poetry. So we're going to look at the different arts and how they intersect, how they connect with mathematics. We'll start off with section 11a today, which is going to cover specifically connections between math and music. So there's actually long been connections between math and music. Pythagoras from 500 BC, so 2,500 years ago, was already looking at the planets. He was looking at the different planets, and he had the idea that they traveled on these spheres, and they obeyed numeric laws, and they emitted these ethereal sounds called the music of the spheres. And so he had this idea that there was a connection between music and numbers that was, in some ways, very much not true, but also really interesting that he started to make this connection so long ago, and now we have so many true connections between numbers and music, and that actually is a thing. There are connections between numbers and music, but he was already starting to get this idea, 2,500 years ago. Other cultures, Chinese, Indians, Egyptians, Mesopotamians, all studied the mathematical principles of sound. What caused different sounds, trying to understand those, looking at the fact that there are principles that just dictate how they work. Modern mathematicians, or current day mathematicians, are still exploring these connections between math and music. They use fields like set theory and abstract algebra, and look at just the different ways that you can create music using math, or you can understand music better using mathematics. There's lots of connections. Nowadays, digital music has established a really deep connection between music and math. We'll talk more about what digital music is and how that works, but that is definitely one of the reasons why there's a really strong correlation connection between music and math. So before we get too much into music, let's talk about what sound is. So vibrating objects produce a sound wave that moves through the air in all different directions. So sound wave is some kind of vibration that moves through the air in all directions from that central location where the vibration happens. You can vibrate strings, so things like violins, cellos, guitars, pianos. Pianos have a bunch of strings inside. So when you press a key on the piano, it makes a hammer hit the string. Guitars, you strum the strings. Cellos, violins, you have your bows that you move on the strings. You can vibrate reeds, so things like clarinets, oboes, saxophones. They have a little reed in the mouthpiece that the person puts in their mouth. And when they play the instrument, they actually make that reed vibrate. That's what makes the sound. Or you can vibrate columns of air. So if you play pipe organs, horns like trumpets, trombones, French horns, and flutes, you actually make a column of air vibrate. So I've got examples, string instrument, reed instrument, horn, air or wind instrument. Those are the different things you can vibrate. So pretty much all music is made by vibrating one of these things to make a sound, and that's how we create sound. So pitch is one of the basic qualities of sound. So pitch is really important because the pitch makes something seem higher or lower. We say it has a lower pitch. If it's like a tuba, it'll be a deeper, richer, it'll be kind of a lower tone. So the pitch, tuba is lower than a flute. Violin is a higher pitch than a guitar. You can tell the difference when someone plays a violin versus when they play a guitar. The violin's higher pitch, it's a higher tone, that kind of thing. Plucking a taut string produces a sound. So when you pluck the string on the guitar, when you put your bow on the violin, you make the strings vibrate. What we see is that shorter strings produce higher pitch, and longer strings produce lower pitch. This is why the guitar is going to make a lower pitch than the violin, because the guitars are typically longer. The strings are longer on them. You have, bass guitars tend to have longer necks than a regular, just acoustic guitar. The string basses are really tall because they want to get really low tones, really low pitches, and that's why they make them really long. So ukuleles, usually have a higher pitch than a guitar because shorter, their strings are much shorter than a guitar. Now you could vary it up. You see people play a guitar and they make higher and lower sounds and stuff. But we're mostly just talking about like the basic sound. If you're not pinching off strings anywhere if you just pluck the string. Again, the longer strings are going to make a lower pitch. Okay. Ancient Greeks knew about pitch. So thousands of years ago, they knew about pitch, but it was centuries before anyone understood it was caused by the frequency of the vibration. So for a string, the frequency is the rate at which it moves up and down. So frequency is how fast the string moves all the way up and down. A string that moves up and down 100 times each second has a frequency of 100 cycles per second. So we use CPS, or cycles per second, for pitch. So 100 cycles per second is equal to vibrating up and down 100 times. So you're looking at a string that's going from the top of its side to all the way down. It's going up and down. The full length up and down is going to be one cycle, and so the number of times it does that in a second is going to be its frequency. Higher frequency gives a higher pitch, so if it moves up and down more times per second, that's a higher pitch. A violin string vibrates at a higher frequency than a guitar string. So when you have a shorter section and you're vibrating up and down, it's not as much of the string to move. It usually doesn't move as far, so you get a higher frequency. So like the violin is going to have a shorter frequency, shorter string, higher frequency, than the guitar has a longer frequency. So higher frequency equates to higher pitch. Lower frequency would be lower pitch. Fundamental frequency. So the fundamental frequency is the lowest possible frequency the string can have. So it's the lowest possible frequency. This occurs when the string's whole length is vibrated up and down. So this is when you take your guitar, you're not pressing, with a guitar, a lot of times you put your fingers up here at the top and you kind of hold down strings. And the way you put your fingers and where you hold them down will change the frequency, it'll change the pitch. So if you don't hold down any strings, you just pluck the string without having any fingers up here holding it down, that's the fundamental frequency. You're getting the lowest pitch that string can make in its its configuration right now. If you do hold down a part of the string, then you've shortened the string because you're not playing the whole thing because it's being pinched off at a point. Then you wouldn't get the fundamental frequency. So the fundamental frequency, again, is when you vibrate at the lowest possible frequency and the whole length is vibrated up and down. Every string has its own fundamental frequency. So every guitar string, all the different strings on the guitar, violin string, all those guys, they have their own fundamental frequency, the lowest which they'll make. It's determined by length, density, and tension. So length, again, like we said, the guitar versus the violin. The guitar is going to have a lower fundamental frequency because it's got longer strings typically. Density changes what the fundamental frequency is. So if you have a guitar with synthetic strings, or if you have like a violin with horsehair strings, or if you have metal strings on your electric guitar, all those different types of strings are going to have different densities and are going to change what the fundamental frequency is. And the big thing is tension. This is why all these guitars have little knobs on the top, because what you do is you just twist that knob and it tightens or loosens the string. The tighter the string, it's going to change the fundamental frequency. If you loosen the string, you change the fundamental frequency. So you change what note it's going to play if you just pluck it without holding anywhere else. And then of course, it also will change all the other notes too. So like if you start pinching off parts of the string, if you pinch it at different points, you're going to change and get different notes. But because you have a different starting note, when you change the tension, all those other notes are going to change as well. Reed and wind instruments have fundamental frequencies, but they're related to like the length of the air column being vibrated. When you're vibrating with the reed kind of vibrates and makes the air vibrate. The wind instruments like the horns and stuff, you can actually change the length of those columns being vibrated. So they have fundamental frequencies as well. We're going to focus mostly on strings because they're kind of the easiest to talk about. So harmonics. Harmonics have frequencies that are whole number multiples of the fundamental frequency. So these guys are whole number multiples. It means like twice as much, or 3 times as much, 4 times as much. So they're not going to be like 2/3 as much, or half as much. They're going to be like whole number multiples of the fundamental frequency. Notice this means that they're always going to be larger. They have higher frequencies than the fundamental frequency. Because if you take it and double it, or triple it, or 5th or 6th or 8th power, or 10 times as much, that's always going to be a bigger number. So these are going to be higher frequencies, they're going to be higher pitches, but they're going to be whole number multiples of the original one. You get these, you produce harmonics by vibrating half, a third, a fourth of the string. So you take the string and you pinch it off halfway through, and you double the fundamental frequency. If you pinch it off a fourth of the way through, then you end up vibrating this, fourth, you get 4 times the fundamental frequency. So you vibrate just a fraction. These are called unit fractions, where they have 1 on top. So like a half, a third, a fourth, these are unit fractions. You vibrate a unit fraction of the string, a half of the string, a third of the string, a fourth of the string. Vibrating half of the string doubles the frequency. Vibrating 1/3 of the string triples the frequency, and so on. So again, here we cut it in half, we double the frequency 2 times. Here we cut it in fourths, it's fourth, and we pinched a fourth, and we vibrated right there, we got 4 times the frequency. And this is what happens with your guitar. You take your guitar, I showed this picture here, and you pinch it here, and you vibrate this bottom piece, and it's going to make the kind of same vibrations up top, but really you're pinching it right there, and you make this vibrate down here, and this is a third of the length, so you're going to get a harmonic that's going to be 3 times the fundamental frequency, because you pinched it a third of the way up, and then plucked it down here. That's why when you see those people play like electric guitars, they pinch it really low to the bottom, then they're cutting into a really small fraction, like a fifth, a first, or an eighth, or whatever. Then they get a lot higher sounds because they're taking that pitch and going to the fifth times 5 times 8. Because the shorter the piece, you're going to get basically a bigger number on the bottom of your fraction. You're going to do a fifth or an eighth or a tenth, and the bottom number, once that gets bigger, you're going to do a bigger multiple of the fundamental frequency. Reed and wind instruments can also produce harmonics. They do this by reducing the length of the air column. They use valves. So if you've seen someone play a trumpet, they have little fingers, valves that they push down, and pushing down different combinations of the finger valves, will vibrate different columns of air. If they're doing this with like a reed instrument, like a clarinet or a saxophone, they have holes on the side of the instrument, and they cover up certain holes, and that will produce a different harmonic. That's would be that with the reed instruments, just by covering up different holes. Okay, so for example, say you have a string and its fundamental frequency is 1024 CPS. So that's the lowest it goes. That's its fundamental frequency. You can't get any lower than 1024. What are the frequencies we get by doing a half, and then we'll do a third? So if I do a half, I take this string and I mark it halfway through, so that's half. Remember what that does is it's going to double the fundamental frequency, because now when I vibrate, I'm vibrating this piece. That piece is going to vibrate as well, but I'm vibrating like one piece, and this piece, because it's shorter, it's not going to have as far to go up and down, so it's going to go up and down faster. Because before, when you vibrate the whole string, it has to go all the way up and down. I don't know if you've ever seen this before, but if you pinch off a string and pluck it, because it's so shorter, it's a little tighter. It's not going to vibrate as far, so it's going to vibrate faster back and forth between. So by doing it half, what we do is we take that 1024 and we multiply it by 2, and we get 2048. That's the cycles per second. The frequency for a half. If we took, pinch it off halfway down. So you take your guitar, find the halfway point on the string, and then you pluck the string, you're going to double the fundamental frequency. If you do a third, so now you're taking it and you're marking it, a thirds, and you pluck this part, so at a third, then this one, it's going to be even shorter, right? Because we plucked it off shorter. So it's even less of the string is being vibrated. So because it's shorter, again, it's going to cycle back and forth faster. So to do a third, we take that 1024 and multiply it by 3. It's going to triple the cycles per second. So what do we get? 2, carry the 1, 6, 7, 0, so like 3072. Hopefully I did that right in my head. And that's the cycles per second. This would be 3 times that amount. And again, because we did it to a third the length, we multiply by 3. So whatever the bottom number is, you're just multiplying by that number, and that's the new cycles per second. The shorter the piece you pinch off before you pluck the string, the higher the cycles per second is going to get. So, and the higher it gets, the higher the pitch sounds, and that's what happens. Okay, Now, ancient Greeks noticed something. They said that pairs of notes sound pleasing and natural. These two notes, they sounded really good together. They really like the sound of them. They said that they feel natural. They feel nice together. And they said that these correspond to what we call an octave. An octave is equivalent to doubling the frequency. So this is really important because we'll see octave like show up on the test on the learning sheet. Octave is when you double the frequency. So basically when you take that string, pinch it halfway, you double the frequency. That's called an octave. A good example of octaves is the piano keyboard. So on the keyboard, on your piano, there's every 7 keys, the frequency is doubled. So you start off with, we call it C, is like the middle key of the keyboard. And we like to use letters, so we do C, D, E, F, G, A, B, and you'll see we go back to C, because after G, they start over at A. And this will repeat, like the next letter would be D, and that'd be 7 away from that D. Every 7 keys, what you'll see on the keyboard is that once you get to the 7th key, you've actually doubled that previous key you started at. So this key over here is double the frequency of this key. So like this one was middle C on a keyboard, which is 260. So say that was 260. Then this C over here is going to be 520, which is going to be double the frequency. That's how that would work. So this would be like 260 here. Then this would be 520. Now a real keyboard has lots of keys. So go beyond this. You'd have a whole bunch of C's. But every time you hit the next C, you've doubled the previous frequency. In fact, the next C after this one, the next RC, would be twice this 520 C. It would be 1040. If you went the other direction, so this C is in the middle, right? If I go down, the C below this one is going to be half the frequency, and that would be 130. You'll notice with this, we'll see this a lot here in the next couple sections or pages, that when you go up the keyboard, your frequencies are getting higher, and so you're going to multiply to get higher, and then when you go down the keyboard, your frequencies are going to get lower, and you'll divide to get lower, and that's going to be kind of the idea. So to be ready to find octaves, here, for example, this tone has a frequency of 4020 CPS. If I want to find the octave, I'll do octave below. Let's say octave above. I'll grab one more color. I can do 2 octaves above. We'll do that way. Okay, so 1 octave below. I want to take this one. I want to go down an octave. Well, I'm just going to take the number. And octaves are always either doubling to go up or dividing by 2 to go down. So in this case, it would divide by 2, and that would give me the next octave down. So it's going to be 2010. That is the next octave down. So that's 1 octave below. So octaves are pretty straightforward because you're doubling to go up, you're just dividing by 2 to get down. That's all you have to do. We also want the octave above 4020. So 1 above. Again, we're doing octave. So I'll take 4020, and I'll double it, times 2, and I get 8040. That would be the next key up. So like, say, I don't know what 4020 is, but say it was a B. This would be the B below. That's the next B down. This would be the next B up. That's what it would be. It's going up by an octave, so we double that original one. If I wanted to go 2 octaves above, so 2 above, well, then there's 2 ways you could do this. One, you could just take the 4020 and multiply by 2 times, right? Because I want to double each time I go an octave up. So I want to go 2 octaves above, 1 octave doubles, the next octave doubles. So take this times 22, I get 8040 times 2 more, and I get 16080, and that would be my answer. So you just multiply by 2 twice. So you can just calculate 4020 times 2 times 2. Other thing you could do is say, well, I know 8040 is 1 octave above. I want to go 2 octaves above, so just go another octave. So I just take 8040 times 2 and get the 16,080, which I kind of used when I was doing the math, but that's the idea. So octaves, again, every time you go up, you double. Every time you're going down, you divide by 2. So if I went from this octave and went down an octave, it would be this one. You can see if I divide this by 2, I get 8040. I'll go down an octave, I take this, divide by 2, I get the 4020. Go down one more octave, divide by 4020, and by 2, I get 2010. Or I can go vice versa, double to get 4020, double to get 8040, double to get 1680. So octaves, it's all about just doubling or dividing by 2. So, this is the idea. We said these are nice. That's the reason why they said, okay, every 7, I'm just going to repeat the letters. Because they said after you get to that 7th one, when you get to that sound, you're getting to this nice sound. It really kind of fits, it blends well. They have this connection, and it's because of the doubling, the octave doubling. Okay, let's talk about scales. So musical tones that span the octave. So they go from from the C to the next C. They're called a scale. The Greeks invented a 7-note diatonic scale. So they basically said between C and the next C, we're going to have these 7 notes, the A, B, C, D, E, F, G. That's the diatonic scale. It's been around for a long time. So the Greeks invented the diatonic scale. It's basically the white keys on a piano. So if you take your piano and you just look at just the white keys, that's the diatonic scale. Now back later, Johann Sebastian Bach adopted a 12-tone scale, which actually uses both the white and the black keys. So now, instead of just doing the white keys, he said, I'm going to include some more notes. I'm going to include some notes like this note between C and D that's either called C sharp or D flat. The key between D and E, which is D sharp or E flat. You'll notice the sharps, it's going up, so from D to D sharp. Flats is when you go down, so from E to E flat. You can use either one. They're interchangeably. They mean the same note. But in music theory and writing music and stuff, there's certain situations where you might kind of want to use one versus the other. It might kind of help people think about it a certain way. There is none between E and F. E and F are a little special. There's no half step between them. No like black key. F and G have this F sharp G flat. G and A have G sharp A flat. A and B have A sharp B flat. There's nothing between B and C. So if you had a C over here, there'd be none between it. So that's kind of how the keyboard looks. I can show you, there's the previous ones. Yeah, there's nothing between B and C and nothing between E and F. That's how that would work. These are just two options for scales. There's actually lots of ways you can do scales because you can pick out lots of frequencies between C and the next C. When you double, you can cut it off into smaller and smaller pieces. You don't have to double. We've done 7 in the past. We've done 12 now. But other cultures actually use the other ones. So in Africa, there are 3-tone scales. So all the way between C and C, there's only like 3 tones. Instead of having 7 or 12, they only have 3. In some of their music, they only use so many notes before you repeat or on the next octave. 5-tone scales have been used in Asia, so like China and stuff. They have used 5-tone scales traditionally. Some 24-tone scales have been used in the Middle East. I believe, I read this, I don't know if it's totally true, but I believe that part of the reason why the 24-tone scale was adopted is to kind of make it easier to use like European instruments and Middle Eastern music, kind of like combine those. And then there are some people nowadays that use 19-tone scales, go beyond these 12 tones when creating contemporary music. So you can use all kinds of different tones. Again, the more tones, it means there's more notes between like C and C. So you're playing like in between those. That's why if you're used to like 12-tone scales of like European music, sometimes you'll hear, other music like the 24-tone or the 19-tone, sound kind of weird or off to you because you're not used to hearing some of these notes, the notes that kind of fit between the notes we're used to. That can happen. A lot of times people that are used to one scale will kind of get, think that another scale sounds really odd. It's because it's using notes they're just not used to using. Okay, half step. So on our 12-tone scale, we're going to focus primarily on the 12-tone scale. Consecutive notes are separated by a half step. So between like C and C sharp, between C sharp and D, between D and D sharp, between D sharp and E, between E and F. Each one of these is going to be a half step. This one's kind of weird. Like I said, E and F, it's only half step between these white keys. Usually it's a half step between the white and the black key, but it's a half step between each of these. So this is a progression like from C to C sharp to D, D to D sharp, D sharp to E, E to F. Between each of those is a half step. So consecutive notes are separated by half step. For each half step, the frequency increases by the same multiplicative factor. So there's a number you can multiply this note by, and you get the next note. And you multiply again, you get the next note. You multiply again, you get the next note. So it's called the multiplicative factor F. It is how far you have to go, what you have to multiply by to get to the next note. So every time you go up to the next note, you're multiplying by that F, that frequency, that multiplicative factor. Over an octave, the frequency doubles, right? We know that over 12 steps, when you go from C to C, you double the frequency. So whatever this is, this C is going to be twice that. Since 12 half steps, you see there's 12 F's down here, 12 half steps occur in the octave, we can find this multiplicative factor. We actually solve it and figure out what it is. So we say, okay, well, F times F times F times F, 12 times, would give us a doubling, because multiplying by f 12 times would give us the same thing as if we just took c and doubled it and got this next c. So f to the 12th gives us 2. If we take the 12th root, so take the 12th root of both sides, we basically find out that the multiplicative factor is whatever the 12th root of 2 is. It's not a nice number. It's one of those irrational decimal numbers. It goes on forever and ever and never repeats. It ends up being about 1.05946. We'll use that as an estimate. We're not going to use the exact 12th root, because that's kind of weird to work with on a calculator stuff. So this is the estimate, and that's pretty good. It's going to get us pretty close to the answer most of the time. So that's the frequency. Back in the day, they didn't have like decimals and calculators. So when Bach and Beethoven, all them were doing their music and stuff, they didn't have nice decimal fraction calculators and stuff. So they had to do this a little differently. But now that we have computers and tuning machines and all that kind of stuff, we can use the kind of exact decimal, the kind of the decimal number. It's not exact, surrounding it, but yeah, that's the idea. So using this 1.05946, we can calculate the frequency of every note on the 12-tone scale. So once you know the first note, you just multiply by 1.05946, you get the next one. And you can multiply by 1.05946 and get the next one. And multiply to go up, and we divide to go down. So if I want to go the other direction, if I want to start up here and go down, I would divide by 1.05946 for every step I go down. So multiply to go up, and divide to go down. So this is the chart. This is starting at middle C. So we talked about middle C. This is like the middle of your keyboard. Middle C has a frequency of 260. If I go up to the next note, which would be C sharp, I would multiply by 1.05946, and I get the next value. A lot of these are rounded because they give you a decimal when you multiply by this decimal, so they'll be rounded to like nearest whole number. If I want to go from C sharp to D, I multiply by another 1.05946. Now, to go from C all the way up to here, I'd actually multiply by like 1.122. I'm not really going to worry about these other fractions or decimals so much, because we can just do it in multiple steps. You go from here to here to here, just by multiplying by 1.35946 over and over again. But that's what they're giving you here. These numbers are just telling you, like, okay, if I want to go from here all the way down to here, I can multiply by 1.122. If I want to go all the way to D sharp from C, I can multiply by 1.18921. Now again, these decimal numbers, they didn't use them back in the past. So what you'll see here is they have some fractions, and they're not exactly equal. That's why I put these little wavy equals. But back in the past, a lot of times they would use these whole number fractions because it'll be easier to work with than like decimals and stuff. So people that tried to go from a C to an E might just multiply by 5/4. We'll talk more about that later, but that's what these whole number fractions are. Okay, so middle C is 260, multiplied by 1.546 gives the next higher tone, right? When we multiply, we go up. Whole number fractions are commonly used approximations. A lot of times people use these as kind of estimates, ways to do it without having to use like fancy calculators or computer tools. The next C, so C up here is 1 octave, and that's double, right? So you can see if you go all the way from the C of 260 all the way to the C of 520, that is twice the frequency, and that's a whole octave. Consonant tones. So these names in parentheses right here, like 7th, octave, 4th, 5th, those are called consonant tones. They have frequencies that are simple ratios of the original value. So like the 6th is 5/3, the 5th is 3/2, the 4th is 4/3. So that's the one where you can use these nice simple whole number fractions. Again, these are approximate, they're not exact, but back in the day, that's what people used all the time. You can see how you can't really do that with like D and D sharp. These guys don't have those approximations. There's other ways to calculate them that they did back in the day, but what they did back in the day is they'd say, okay, well, if C is this note, then E is going to be times 5/4, F is going to be times 4/3, G is going to be times 3/2, and then they go back and figure out the rest of them. That's probably part of why back in the day, if you wanted to tune pianos and stuff, you had to go through like a lot of training. Nowadays, it's a little bit different because you have computer tools that help you do that. But these are the big ones. So the 3rd, the 4th, the 5th, the 6th. Second, notice we don't have a nice whole number ratio for, so we're not going to worry about second so much. And then like 7th, same thing, doesn't have a nice whole number ratio, so we're not going to worry about that. We're just worried about using these 3rd, 4th, 5th, 6th. I will work with those. So we'll use both that 1.05946. We'll also end up using like these 3rd, 4th, 5th. So I'll kind of see a little bit of both. Okay. So in using this, let's actually find something. Let's find the note with this. Above the C with frequency 520. So that's the one at the bottom of this chart. This chart, I don't know if you noticed, it's kind of upside down because we're really starting with the lowest note because that's the lowest CPS and going up to the highest note 520. To me, it should be upside down. It should be the other way, right? You should start with the bottom and go up to the top. But we're starting with the lowest and going to the top, the highest frequency down here. So it's a little backwards, but we want to find the next note in the sequence, which would be C sharp. The C sharp after this one. So it's going to be C sharp. Because we want to just go one note up, we just use 1/2 step. And 1/2 is just basically multiplying by that 1.05946. Again, this number I'll give it to you on the formula sheet. I think I have it with me. I'll show you on the formula sheet. Here it is. It's right on the table, 1.05946. I even put it on the back side that each half step is 1.05946. So I would just take this 520 and I'd multiply it. That's 1.05946. Multiply that out, 520 times 1.05946. And I get 550.9, so it's about 551. You're rounding appropriately, right? Because 0.9 is bigger than 5, so we're going to have enough to round this up to the next place. We'd say it's about 551. That would be about the frequency of the next note. There's going to be a little bit of rounding here, error here, and my lab is built to account for that, so that's not a big deal. But sometimes if you get it wrong, you may have to watch your rounding. That might be why. How about I want to go to the note below middle C? So remember, middle C is 260. That's the middle C right here. That's what we're talking about when I say middle C. It's the C that's 260. On the start of this chart is the middle C. I want to go below. Well, that just means instead of multiplying, now I'm going to divide. So I'm going to divide by 1.05946. So I take 260, divide it by 1.05946. Get the next one down, which is 245.4, which 0.4 we don't usually round up. So we'd say this one would be 245. I should say about again, wiggly equals, because we did have to round that 0.4 off. So it's about 245 again. This would be cycles per second. And the note below this C, so would actually be a B. So this would actually be a B. I'm not going to ask you, test you, oh, did you figure out which note that is? Is it B or what? But I do want you to be able to find these. So the CPS, that's what I'm going to look for. Here's the middle C. What's the next down? The next down is 245. Should be going smaller, right? Because lower frequency. It's a lower tone, lower pitch. That's what's happening when we go below versus when we go above. When we go above, we're going up. When we go below, we're going down. So that's kind of the difference. And you go up, your frequency should get higher. When you go down, your frequency should get lower. Now these were just using the half steps, but we also mentioned those consonant tones. So the consonant tones are when you want to increase or decrease by this fraction value. So first off, they want to start with A sharp. So we're going to look at the A sharp on our chart, which is actually 463. So A sharp here is 463. And they want to raise by a fifth. So raise by a fifth means we're actually going to use the value 3/2. So the fifth, we're going to take 3/2. We're not going from C to G, right? We're not doing this interval from C to G. We're doing this many steps. We're starting with A sharp and going to some number further higher, frequency over here. But the fifth just tells us, the fraction. One, two, three, four, 6, 7. It's like going 7 half steps. But I'm going to start from A sharp and go 7 half steps. And the fifth is really just going to tell me which fraction to use. So if I want to raise by a fifth, I'm going to use the 3/2 fraction, because that is a fifth. A fifth is doing the 3/2. So I take this and I'm just going to multiply it by 3/2. That's how you do that. If you want to raise by a fifth, you multiply by 3/2. I'm going to do 463 times 3 divided by 2. I guess I could put that as a fraction, or as I put it as a division. Doesn't really matter. Calculus is the same. So I did 3 divided by 2. So I'm used to using divisions. If you want to do 463 times and do 3 fraction 2, you would get the same answer. So you can see it really doesn't matter which method. This one does give you a fraction, not a decimal, and I would probably want the decimal in the test. But if you ever have that, this calculator does let you turn things back into a decimal by using the second key and then hitting this table button. And now I'm going to have something says, okay, I'm going to turn that into a decimal. If I hit it enter, that's what it does, and you get that 694.5, which is actually what I had up here, 694.5. So this would be about 695. We're going up by that fifth, you multiply by 3 halves. To lower, we just divide as a multiply. So I'm going to take the note B, which B on here is 491. So 491. I'm going to divide by 6. Well, 6, constant tone 6 is when you're using the fraction 5/3. So I'm going to divide by 5/3. So I'm going to take this fraction, this 491, divide by that fraction 5/3. Now I get my answer. So if you're using a calculator like this, again, clear this up. I'd take 491, I hit my divide button. I would, you can use my fraction button. I could do 5 fraction 3, and that would give me my answer. Again, if it gives you this, you want the fraction, the decimal answer, second, turn it into a decimal, and you get 294.6. So notice that this is lower because we divided 294.6, which would be about 295. And because we lowered, we should expect a lower pitch, a lower frequency. Because we start with 491, we go down. Divided by 5/3 works. Note that you can also do this lowering. You can actually, there's a tricky way to do it, where instead of dividing by the fraction, you can actually multiply by the reciprocal. So if I take 491 and I just multiply by this fraction flipped over, remember from grade school that dividing by a fraction, you can always do by multiplying by the upside down fraction. If I multiply by 3/5, I get the same answer, 294.6, which rounds to 295. So there's two options to do this. You can either divide by the fraction or you can multiply by the flipped over fraction. So you might see, like my math lab or me, use that sometimes, where instead of dividing by 5/3, you might multiply by 3/5. So you could just put same as 491 times 3/5. So just a little, that's going to give you the same answer. All right, so that's doing the constant tones, these nice little whole number fractions, and doing the half steps, right? You can go by a single half step, up or down, up, multiply, to go down, we divide. Same thing with the fifth, sixth, the consonants, tones. We multiply by a fraction, go up, we divide by a fraction, go down. Okay, so these musical scales we're going up and down are actually a form of exponential growth. I was just teaching exponential growth in my algebra class, and we're talking about how as you go higher, things grow faster and faster with exponential growth, and that's what happens with a keyboard. So this means, in this case, what happens is every time you go up a key, you're multiplying by that same multiplicative factor, and when you repeatedly multiply like that, you're doing a form of exponential growth. Things are just getting larger and larger. You'll see that the tones towards the top of the keyboard are going to be really big numbers versus the tones at the bottom where they're going to be pretty small. So if you want to find a specific tone on the keyboard, you know your starting tone, and you want to say, I want to go up this many half steps, get to a different tone, and you want to find that tone, you can use a formula for it. So there's actually a formula to go up and a formula to go down. We've got two different formulas, one for raising, one for lowering. And to do these, you need to have some labels here. So first off, the starting frequency is to be Q sub 0. We like to use a little sub-zero on math equations to indicate something at the beginning, the original amount. So this is the starting amount, this is the starting note. The target frequency is just going to be Q without a 0. So that's where we're trying to get to. It's not the starting amount because it's not a 0. And it's going to be the number of half steps that they are, the distance between the two. And you can use the formula. If you want to raise, Q is going to be equal to Q sub 0 times that multiplicative factor to the nth power, which basically you could just do by taking that 1.05946 to the nth power. And that's what I'll have on the formula sheet like this, where my amount I want to get to, the note I'm trying to get to, we'll just take the starting note times 1.500546 to the nth power, where n is how many half steps you want to go up. If you want to lower, do the same thing, Q, but now instead of multiplying, you divide, because now we're going down. So we take that same 1.05946 to the nth power, we divide by that amount to lower the note. So we're going to use the formula this time. Find the frequency of the note 7 half steps below middle C. So remember, middle C is 260. You can look it up on the chart. I always give you like notes that you can look up on the chart when doing like, the test. So middle C, 260, it's right there on the chart. 260, I want to go 7.5 steps below. So this is my starting amount. That's my Q sub 0, 260. Because I want to go below, we want to lower. I'm going to divide by 1.05946. And then the power n is just how many half steps. In this case, n is 7. We put that 7 power. That'll take this, it'll move it down 7 steps. And that'll give us our answer. Just type that in our calculator. So I'm going to do 260 divided by 1.05946 to the power of 7. And we get about 174. So 174. Yeah, it's about, because I rounded, right? 173.5 rounds up to 174. But that's about our answer. That's the frequency I would put for this. So we lowered, right? We went down. 174 makes sense because we have a lower frequency. And again, the number of half steps is what this power is. It's the number of half steps. Say I want to do the same thing, but now I'm going to find it above. So now we're actually going to go raise. We're not going to go down, we're going to go up. I want to do a fourth. They say a fourth, but that's just 5 half steps. And they're pretty nice in the homework. They'll do this too, where if they say fourth, fifth, in this situation where you're supposed to be using the formula, they'll tell you the number of half steps. Now, if I had just said raise by a fifth or lower by a fourth, and didn't talk about the number of half steps, then I wouldn't be talking about using the formula. I want you to use the formula in this case. But we saw on the previous page where I just said raise by a fifth or lower by a sixth. There's nothing mentioned about the formula. I don't tell you the number of half steps. That's why I want you to use these. So on like the test or the homework, you'll see these kinds of problems where you're just using the whole fractions like that. Or you might see problems where they give you the number of half steps and mention the formula, then they'll want you to use the formula. So in this case, the formula we want to raise, so we're going to multiply the raising formula. Still 1.05946. And then the power here, we want to raise a fourth, 5 half steps. That's our n. So we're going to raise by 5. I realized I just made a mistake. I don't know why I started with 260. I think I looked up here and saw the 260. No one said we're starting with middle C this time. We're actually starting with the G above middle C. So that was a mistake here. Sorry, that was my bad. So G above middle C, look at my chart again. That's this G. There's middle C. This is the G that's above it. So we actually wanted to start with 390. So whoops, that was my mistake. Sorry about that. This is supposed to be 390. It's important to have the right starting number. I made a mistake there. So 390 is my starting number this time because we're starting from the G above middle C. And then we're still doing 1.05946 to the fifth because that's that number of half steps. And we're raising, we're going up, so we multiply. And that's how I get this. So I do 390 times 1.05946 to the power of 5. That would give us 520.5, so about 521. So about 521 if you round that. Again, we're going up. That makes sense. You'll notice that 520 is a little bit off. Like the C is typically 520. So we went from a G, we actually went up pretty close to C. Again, that's the problem with using a decimal like this. Is there's a little bit of rounding error, a little bit of rounding here. So my math app should be built to take this, okay, 520, 521. In fact, there's a problem where they kind of illustrate how the fraction values really give you slightly off amounts, and they have you do a whole bunch of raising and lowering and show you how the final amount's not equal to like the starting amount because these fractions are very approximate, not exact. So let's show you a little bit of rounding errors on the homework questions. On the test, I'll be pretty forgiving, right? Because I'll know that these are using a decimal and you're supposed to be rounding. Just make sure you round appropriately. 0.5 and above should go up, and anything below 0.5, 0.4 down should go down. Should, not move the value up. Okay, let's do one more. Let's find the value. I'm going to know a note that's 1 octave and a fifth, 7 half steps above D sharp. And we're going above, so again, this is a raise. We're going up. So D sharp, first off, the D sharp above middle C. D sharp is 309. So that's our starting amount. Hopefully this time I'll remember to start with the correct starting amount, 309. This one's a little tricky. When I first looked at this, I was looking at the homework because they changed this actually when they just recently updated the book. I saw this and said, oh, we're going to go 7 half steps. Well, no, they actually are saying that a fifth is 7 half steps. So if you look at a fifth, you can see here that a fifth is going up 1, 2, 3, 4, 5, 6, 7, which we counted before, right? That's the fifth. That's 7 half steps. They want us to go both an octave and a fifth. They actually want us to go these combined. So they don't want us to just go 7, because if you remember, an octave is actually all 12 half steps. When you go from C all the way to C, that's 12 half steps. They want us to go to 12 plus 7. They actually want us to go 19 for our whole octave plus 7 more half steps. So we're going like pretty far. We're going, all the way past this set, past the next set, and then go a little bit further. So that's what they want us to do is 19. So even though it's tricky, it says here like 7 half steps, and you're like, oh, 7's my end. No, because I want to go an octave and a fifth. This is just telling you how many half steps are in a fifth. I saw some more questions like that, so I'm going to put one like that in here. Just kind of point out that that happens. Okay, so n is 19. I'm raising, so I'm using the multiplication version of it, where I multiply by 1.05946 to the nth power. So take my 309 times 1.05946, and my power here would be 19. And that'll get me up an octave and a fifth. 309 times 1.05946 to the power 19. And that's what I do. So I get 926. My answer, 926. Again, that's approximate, because I rounded that 925.9. 0.9 tells you to round up, so I got 926. So that's the different things. That's really the math of this section. The math is just about taking these tones and finding the lower and higher tones. You should be able to go by octaves, where you double. Get this on for a sheet. Remember the octaves, you double or halve. Double to go up, divide by 2 to go down. You should go like individual half steps, where you just multiply to go up and divide to go down. You should be ready to use the certain number of half steps. This is the formula where you take your frequency of your note and you multiply by 1.05946 to the nth power, or you divide by 1.05946 to the nth power if you're lowering, and then be ready to use the fractions, right? So for example, a fifth, 3/2 times the frequency. If you want to lower, you can do the reciprocal, right? 2/3 times the frequency, or you can just, take the frequency divided by 3/2. But that's what I have on the formula sheet. So this is what the formula sheet's going to look like. Just kind of reminders on like how to do the consonants, the number of half steps, a single half step, and the octaves. And you get this full chart. This full chart will be on the back of the formula sheet when you're taking this exam. So that's what you'll have for outputs. Last thing, I want to talk more about the modern, way that music and tones interact. So to talk about that, we need to talk a little bit about how music, tones, what they look like, what they are. So simple frequencies are the building block of music, these simple like waves. But actual frequencies of music are way more richer and complex. They have a lot more depth to them. They're not just these simple waves. If you ever looked at like a program like Audacity, where you can like look at the sound waves and stuff, you see there's a lot going on with them. This is the reason why. So for example, you pluck a violin string. So when you pluck the string on the violin with your bow or with your finger, whichever way, it vibrates the top of the violin because these are connected to the violin, so they vibrate. There's also like rib pieces and like the edge piece that connect the front to the back, and so those all vibrating the back of the violin. So the front of the violin, the back of the violin, they both vibrate. They make this resonating chamber within the violin where the sound gets bounced back and forth between the two walls, and it creates and amplifies lots of harmonics of the original tone. So you play the note that you played, but because your violin, if it's made well, has the front and back and all these connections and stuff, it actually makes all these harmonic tones as well. It's kind of the same idea, like if you've ever seen a choir walk into like a big cathedral with all the different like tall parts of the cathedral, and they sing a song, and it just sounds a lot deeper and richer, and it just sounds so good. It's harmonics is what's happening, because their sound waves of their voice is bouncing off all the different parts of the building, and it's creating all the harmonics. So you're getting all these higher pitched tones. So harmonics make the music deep and rich, and they make it sound good. So a better instrument has better harmonics. Your book talks about like Stradivarius, how we still don't understand why, but Stradivarius' like violins were so well made. They have a much more deep and rich sound than pretty much any other violin. No one's been able to really replicate how good his violins were, and we can't even really explain why mathematically his violin sounds so much better, but we know it has to do with they create better harmonics. They create more and better harmonics. So all instruments, no matter whether they're cheap or expensive, whether they're string or reed or wind instruments, they do create complex sounds with lots of different harmonics to them. Again, the better the instrument, the more harmonics, the better the harmonics. The wave below illustrates a typical sound wave frequency for like music. So music might look like this. So this like might be what your sound wave looks like. What we found out is it's actually a combination of multiple simple sound waves. So you can kind of see here there's these high peaks. They go along with this big row. But then you also have like these middle peaks down here, which kind of go with the middle row. And then you got the really small little peaks, and they go with the bottom row. And they're all combined together so that now you've got one sound wave with doing all these little bumps and wiggles, but it's really just made up of lots of smaller sound waves combined together. And so it was in 1810 that French mathematician Jean-Baptiste Fourier, Joseph Fourier, first discovered this principle, that any musical sound could be expressed as the sum of simple harmonics. He figured this out not that long ago, right? We haven't known this for super long. In the world of math, this is not that long. Just 200 years ago, we finally figured out, oh, this is how musical sound waves work. Now we understand this even better because we studied for 200 years, but back then, it was a big deal just to figure that out. That's how come music sounds so rich and complex, and then that's how it works. It's actually made up of all these different individual sound waves. Now, so far we've been talking about sound in terms of waves. And when we treat music as waves, think about it like the just wave motion, the vibration of the air or the string, we're working with what's called the analog picture of music. So analog music is music that's consists of waves, music consisting of waves. And up until the 1980s, all music was recorded with analog, meaning that the actual sound waves were recorded in the medium. So if you went and bought a cassette tape or a record, they actually had the sound waves physically stored on those things. So like records, they basically have a little path for the needle to follow when it goes around the record, and the path would wiggle back and forth or up and down or both, depending on how the record was made. And that wiggle up and down, back and forth, that would be the sound wave. So by going up and down, you change the volume, the intensity of the sound, and it would basically reproduce the sound wave. Cassette tapes had basically a magnetic tape inside them, and that magnetic tape was like more intense or less intense at parts, and that intensity reproduced this sound wave. So they had the physical sound wave just stored on them in a different way. So instead of drawing a picture of it, the tape had magnetic intensity, how much magnetism or how little magnetism. Records had basically a piece carved into them. Now today, we don't use a lot of tapes anymore. Some people still listen to records, but most people, most of the time, if you're listening to music, you're probably listening to it like off your computer, off your phone. Then you're doing digital recordings of music. So digital music is kind of the king now. Anytime you listen to music, if you go into a movie theater, if you play music off your phone, play music off your computer, if you listen to like XM radio, anything like that, you're listening to Spotify, music on YouTube, those are all digital recordings of music. So CDs were a big, change where we went from like records and tapes to CDs. That was the big transition. Nowadays CDs we don't see as much, but we definitely still see plenty of digital music because every kind of MP3 you listen to on an electronic device is a form of digital music. So most people listen to digital recordings. So what's a digital recording and how does they come about? So let's look at the last page here. We're just talking about digital process and digital music. So digital recording is made. Music passes through an electronic device. It takes the sound waves and converts them into an analog electrical signal. So this is still analog because it's like a wave, electrical signal that measures the wave. But then they digitize the signal. So when they digitize the signal, they record the data, and usually it's recorded in like binary, like sets of like zeros and ones. And it represents the signal. So basically, when you digitize it, you take it instead of saying, "Okay, now I have the wave." You might have the wave in like magnetism or electrical pulse. That'd be analog. But you take that and say, "Okay, I'm going to record values, numbers, basically data that represents those waves." To make this digital version, the wave is sampled. So you look at the height of the wave at regular time intervals. So you can create a number for each height. The volume is like the wave height. So you record the volume at like multiple times per, over and over again, periodically. Sampling rate describes the number of samples taken each second. So when you go to record and digitize, you have your original wave, you sample it. Now, if you want to sample really poorly, you could sample like 2 points. Okay, sample, and you got kind of close to your wave because you know it's going to like go from the previous point to this point, from here to here. But I want this curve, so you might try sampling more, like 6 points. Okay, now at 6 points, you can see that's closer. It's got more of a curve shape. Here you go up to 10 points, and you see you have a lot more. Well, music is actually typically sampled at a rate of 44,100 hertz, or 44,000 samples per second. So this is like 10 samples, but music, if this is a second of music, there would be like 44,000 samples in here. It's a lot of samples, right? So it's a big deal. 44,000 samples lets us get a really good, precise waveform because we've sampled so much. So sample rate, that's the typical sample rate, is 44,000. That's how many times you measure the height within a second. And then the bit depth for music is actually the number of possible values we can use for the volume. So say you sample 10 times, well, here we only have like so many results. And some people could sample it and say, okay, I only want to go for like 0 to 10. And you have very poor measurement because you only have like numbers from 0 to 10. We tend to use, most digital products uses like 16 or 24 bits. That doesn't mean 10 or 16 or 24 numbers. It actually means 16-bit means you have 2 to the 16th of 65,000 possible values. So when you're sampling here, you can go anywhere from like 0 to 65,536. So it gives you a big range of values from top to bottom. 24-bit even has more, actually has 16 million possible values. So you start all the way from 0 to 16 million for your range of your values. And usually it's not from 0 to something. They usually have like the 0 would be in the middle, and you'd have like negative numbers or positive numbers. So you have like 33,000 above and 33,000 below-ish. And then like this would have like 8 million above and 8 million below 0. So you can have positive or negative height. Your wave's above 0, below 0. But that's how they do it. So, we use bit depth, possible number of values for the volume, and most music is that 16 or 24-bit for possible ranges. So sampling rate, basically we take this wave and we represent it as a bunch of series of little numbers, and we say, okay, what's the height at this point, 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 over and over and over again, over the whole graph. And by using 44,000 samples and giving ourselves lots of options for the height, we can get a really precise measure. This is why digital recording sounds so much more, so good, why it sounds a lot like the real thing, depending on your speakers and stuff. People always get upset about the quality of like digital versus like, some people think that record is the only way to like listen to music because it's still analog. Honestly, it has more to do with how good your speakers are, because this digital processing, we've gotten down to pretty good science. So we know that doing 44,000 hertz and either 16 or 24-bit is going to give you enough musical like values, enough digits that you can reproduce this wave perfectly. As long as you have a good speaker to make the sound, you're going to be fine. So the sampling process is reversed to convert the number back into an analog electric signal, which then drives your speaker to reproduce the sound. Digitizing makes it possible to store your music on CDs or hard drives, or to send it over the internet. Now it's not a physical wave, so I don't have to have like a physical wave on record or on tape. Now it's a series of zeros and ones, a series of numbers. So I can just transfer that series of numbers to a hard drive. I can send it over the internet and do that. So this is the process. So we start off, we have our sound. It's pressure in the air. A microphone picks up that sound and uses what's called an analog to digital converter. So it takes, this voltage from this microphone and sort of turns it into a series of numbers. Those numbers are stored in memory, whether it's on a CD or a hard drive. And then those numbers are converted using what's called a digital to analog converter, or a DAC, back into a voltage. And then that voltage goes into a speaker, which pushes a, the speaker part of the speaker that moves back and forth, creates sound waves. And those little sound waves, and the air pressure, make our sound. And that's what happens. Every time when you go record, like if you make a phone call, this is what happens in a phone call. Because you speak into the phone, the microphone picks that up, converts it to numbers. The numbers are transferred over the wireless connections on your phone. Those numbers then are picked up on the other phone, converted back into voltages, which are sent through the speaker and the earpiece of the other phone. The head, maybe the headphone would just be the ear part of their phone, if they're whatever they're using, and then that moves the air, making this air pressure, making the sound. That's what happens. That's why digital music is such a big deal, because now we have a nice, easy way to take music and get it to someone else. And again, this wasn't around until like the 80s. They started to get CDs, and then later we were able to do this more with MP3. Okay, so now that we have our music stored as memory, as data, as numbers, ones and zeros basically, we can do some digital signal processing. So this allows us to take that set of numbers that we've recorded for our sound, and we can actually look for things that are extraneous, things that are not supposed to be in there. This is why you watch like CSI shows, where they're doing the crimes investigation. They get a little sound clip and they can play it back and they say, oh, cut this part out or cut that part out. Well, someone's using mathematics. They're basically looking at the signal and saying, hey, remove tones in this range, remove this simple wave, remove that simple wave. Like we have sound of the train coming by. Well, we know what that sound of the train is going to look like digitally. Remove that part, see what's still left, and then you get the rest of the sounds. Musicians use it to correct errors. This is where autotune comes into play. So for a long time now, people have been using autotune. So if they're singing their note and they're a little bit off, they're a little bit high, a little bit low, autotune fixes it. Lets us combine different pieces of music. This multi-tracking, where someone records like the guitar piece, someone records the drums, someone records the vocals. And they do it all separately, and then they just combine it together to make one piece of music. That's multi-tracking. And then sometimes people add musical sounds without playing musical instruments. This is where you can like pull up GarageBand. You can take your song and you can say, hey, but I want a cymbal hit here. You just put it in there without actually like having it be part of when you played the music. You say, I want to add to the song. Or you can make your own whole new song. It's all because of digital sound processing. It's all because we've digitized music. So that's what that lets do. Okay, so the big thing for this section when it comes to the homework and the test is being able to get those frequencies, how much you'll be able to go up and down the frequencies using the octaves, the consonant tones, those fractions, and then like the half steps, the 1.05946 and then the 4 with the 1.05946. But it's good to know a lot of this about kind of digital music, how this works. And again, if you wanted to get further in this, there's a lot of mathematics behind this. People have been studying this for years. So there's a lot of programming and computing and mathematics that goes into creating all these things that lets us have such good music quality. Hopefully that was interesting for you and enjoyed that. And I'll see you on the next one. We're getting to math and the visual arts.